Hi, my name is Jean-Baptiste, and I'm going to talk about running deep learning models in trusted execution environments. This work is in collaboration with William Gallagher, Tian, and Robert Walls from WPI. Machine learning models are widely deployed on untrusted hardware, for example, on remote servers for machine learning as a service, or on mobile devices like smartphones or home assistants. Machine learning models are valuable because they are intellectual property, but also they're expensive to train for collecting the data, paying for the computation or the expertise to train those models. And also once a model is stolen, it can be used to mount more complex attack against this model, for example, crafting adversarial examples. A bit of background on convolutional neural networks, or CNNs. They are a deep learning architecture that was designed for computer vision, but then convolutions were also used in different architecture later on. The architecture takes in an image. Here, the size is 224 by 224 for height and width, and you have 3 channels, one for red, green, and blue. And as you go deeper and deeper inside the network, you can see that the image shape, which is actually the activations of different layers, will change. So the width and height become smaller and the number of channels increases. The overall structure of the neural network is convolutions in the beginning. I will give more details about convolutions, but they basically serve as extracting features from the image on different scales. And then the fully connected layers are on top of that. And you can see that as more useful for classification or regression purpose on top of extracting the features. And these models have usually a high memory footprint, and we'll see how this impact this work. Now, our goal would be to run our deep learning models on untrusted machines. And a very intuitive idea here is to use trusted execution environments. I'll give a bit of background about it. It's a hardware-powered feature on recent processors, which give you a few security guarantees. For instance, you have secure execution, so the OS cannot know what's going on in terms of computation. It can see the instructions on the CPU. You have a secure memory area where you can store data, and this is isolated from the OS. And you also have integrity checking for this data. A few more properties about TEEs. The secure memory area is very convenient, but usually pretty small in size. And also there is a slow secure paging mechanism that is used for memory intensive programs. For instance, if you have only 28 megabytes of secure memory, then running deep learning models would require some secure paging as in a normal OS. Secure paging work as explained on the diagram on the right. When somebody tries to access a piece of data in the TEE, we check if the page this data belongs to is already loaded in memory. If so, then the request is served. Otherwise, we check if the memory is full. If not, we can just load and decrypt the requested page. Otherwise, we need to evict the page first. So we have to encrypt it, swap it out, and then we can load a new page in. And then we can proceed and by loading and decrypting the new data. One last comment about TEEs. They are widely deployed on servers, desktop computers, or laptops. If you have an Intel processor, chances are you have SGX installed, which is an implementation of a TEE. And on mobile devices, if you have an ARM processor, you might have access to a trust zone TEE. The main drawback here is that since the secure memory is pretty small and deep learning inference requires a lot of memory, you need to call secure paging a lot, and this incurs a significant performance drop. In this paper, we focus on 2 different bottlenecks explaining this performance drop, and the goal is to optimize the performances when running deep learning inside the TEE. The 2 bottlenecks we're tackling in this paper are page thrashing in convolutional layers and the decryption bottleneck in the fully connected layers. These are 2 separate bottlenecks, but they all come from the inefficiencies coming from the secure paging mechanism. I will start by describing the page thrashing bottleneck. First, some evidence. We measure the latency of the VGG16 model outside the TE and inside the TE for the biggest convolutional layers, so number 2, 5, and 8. Each column represents a TE configuration. The first one is 28 megabytes of secure memory, which is very small compared to VGG's requirement of about 1 gigabyte of memory, and one virtual CPU. And for different TE configurations, we have more memory and more CPUs, actually virtual CPUs available. As we measure the latency, we can observe a huge difference. Here, outside the enclave or the TE, we have only 0.5 seconds of latency, while inside the TE, without modification, we have over 17 seconds. And that's huge. And we can observe the same behavior in most of those enclaves, where we have a big multiplicative factor between outside and inside the enclave. We can also compare these inefficiencies with the size of the input here, 128, 61, and 31, compared with the TE memory. And we can observe that we don't have this page thrashing bottleneck occurring when we have enough memory to fit the layers in secure memory. Then we can try to correlate this latency with the number of page eviction, which is a way of observing page thrashing. And we can see that the number of page eviction is huge, like over 1,800,000 for some layers, and depending on the enclave configuration, we have less page thrashing. So we can make a big distinction between layers where we observe page thrashing and layers where we don't. We have about 10 as a multiplicative factor. Right, now I'll try to give some background on convolutional layers and how they work. You have an input and an output. They have a different height and width, but also a different number of channels, which are represented here. And the way we compute one output during convolution, one output value here, we need to do a weighted sum of one part of the input image. And that part is highlighted in black here. We call that black window a kernel. And to compute each successive value in the output, you have to just slide the kernel to the left, or to the left or down every time. And once you are done with one channel in the output, you just have to start again with a different kernel, so different weights, and you can compute the next channel, and so on. One big inefficiency, and I'm not talking about TEs here, that's a problem we also observe in regular OS, is that since you have an overlap between the different kernel positions, you would need to reuse the same data over and over again. And if you don't take this into account, you have cache inefficiencies. So instead, what we use is the im2qual transformation, which duplicates the input data and put it in a 2D matrix. We can also take all those weights, put them in a matrix form, and we transform this complicated and cache inefficient convolution operation into a very nice matrix multiplication for which we have efficient algorithms. And this is the mathematical form. And here we can note that the transformed input is much larger than the original input. If we have a 3x3 kernel, we have 3 times 3 equal 9. You have a 9 factor of multiplication in size between the original input and the transformed input. And because we're multiplying large matrices together, and we have inefficient access patterns, that's how matrix multiplication works, you have continual encryption and decryption of the same data. You keep bringing in and out the same pages. And this is what we observe as page thrashing. Now, some intuition on how we decided to solve this problem. We chose to partition the inputs in different ways. So we have two partitioning schemes. We have the wide plane partitioning, which is defended in this paper, but we also have channel partitioning, which was proposed by Lee et al. In the Clemency paper. In wide plane partitioning, we split the inputs and the outputs horizontally in horizontal planes, which we call y plane. and you can observe one output Y plane on the right side of this image. And as we can observe on this image and from our understanding of convolutions, when you want to compute one output Y plane, all you need is the three first input Y planes here and all the weights from all these different kernels. So if we decide to split horizontally the input and outputs, we can rewrite the computation as still a weight matrix times the input, and we get an output. But instead of using the whole input, we can just use the three first Y planes. So instead of using the 224 first Y planes, we just use 3, which saves a lot of memory. And we can repeat that process for every output Y plane. Right, now moving on to the channel partitioning, I won't go into too much detail, but here we split the input by channel, and we can compute only contribution to the output. As you can see here, the top right element of the output matrix is computed by using the entire, if you remember, you have to use the entire input and weights to compute one value. And since here you only have access to one channel at a time, all you can compute is contribution to that output. Therefore, here we split the input by channel. We also split the weights by channel. As you can see, we don't use the entire kernel. And all we can compute is a contribution to the output. So we have to keep the output in memory the whole time. Therefore, this method partitions only the weights and the inputs, but not the output. And as I explained before, the convolutional neural network architectures tend to have a varying layer size. So for example, the height and width of the image will decrease when we go deeper in the network, but the number of channels will increase. And this change of shape of the intermediate activations make one or the other of these partitioning more or less efficient. For instance, if we use Y plane partitioning and the weight matrix is very large, we might have inefficiencies. In this case, it would be better to use channel partitioning because we split the weight matrix. But in earlier layer of the network, for example, where the output is very large, channel partitioning would be inefficient because we don't partition the output. Instead, we should use Y plane partitioning. And this is precisely what we do in this paper. We decide to use Y plane or channel partitioning for the most relevant layers. So for instance, in early layers, we'll use Y plane partitioning, and later layers, we use channel partitioning. And all these can be decided beforehand because we have access to the architecture. So we can compute how much memory is required at every stage, and we can make a decision and use the most efficient partitioning scheme on demand. As for the results, we took the same figure as before, same table as before, and we added one row in the middle when we use partitioning in the TE for the same layers. And as we can observe, the inference time, the latency is much smaller when we use partitioning than when we don't. And this is translated also by the fact that we don't observe page thrashing anymore in the TE. As you can see, the number of eviction is much smaller. Sorry. Now, moving on to the decryption bottleneck. The decryption bottleneck occurs in fully connected layers, and here is a bit of background on how does computation work. We still have a matrix multiplication between the weights and inputs to get the output, but this time the input is a vector and the output is a vector as well. Those vectors are pretty small, so they already fit in memory, so we don't observe the same page thrashing problem. However, the weight matrix is usually pretty big. For instance, in VGG16, it's something like 300 megabytes of memory. And so decryption will dominate while doing those computation. For example, in layer 2 of VGG, with the darknet implementation, we observed 1.1 second just for decryption, and then 28 milliseconds for computation, which is much slower than just computing, obviously. So the problem here is, how can we reduce the decryption time? We could try to accelerate the decryption rate, but that would require access to the hardware and to modify it. So instead, we'll focus on a different approach, and we will try to reduce the size of the data that needs decryption. To do so, we use quantization and compression. Quantization, if you're not familiar, consists in casting values to a predetermined set, for example, using 16-bit floats instead of 32 bits. Or we can use lossy compression to store the weights compressed and then decompress them only once they are loaded in secure memory, so after decryption. In both cases, we lose information, so we can expect a drop in accuracy. But from our experiments using the ImageNet data set, we observe that we have no drop in accuracy at all when using 16-bit floats compression, quantization. And when we use compression, we only get significant accuracy drop, so 0.2%, for instance, when we use smaller and smaller compression ratios. And so the limit we choose in our experiment is 5 out of 32 in terms of compression. As for the results, we ran the same experiments as before, but we measured the latency only for fully connected layers outside the TE and inside the TE with quantization and compression, or the unmodified implementation. You can observe a huge increase in latency between the baseline, so outside the enclave, and inside the enclave with the unmodified implementation. And you can see that quantization and compression roughly allowed us to halve the latency as compared to the unmodified implementation. And all that for no to almost no drop in accuracy. As for the end-to-end results, we report those numbers in this table. Each row represents a different T implementation or configuration. So 28 megabytes, one vCPU for the first row. And the different columns are the baseline outside the enclave. And inside the enclave, we have the optimized and unmodified implementations. As you can observe, there is a huge increase in latency between outside the enclave, the baseline, and the unmodified implementation inside the enclave, up to 26 times worse. And once we run the optimization, we can see that we are much closer to the baseline with even 1.09 times the baseline, the best scenario. Right, now time for a small discussion. We want to note that the models, if the models fit in secure memory, then these techniques can appear to become less relevant. For example, in ResNet, the model runs as fast with the partitioning. And also we can expect the T memory to increase over time. But still, those techniques, in particular partitioning, are very useful because if you want to run different TEs concurrently on virtualized machines, you still have to share the secure memory area between different TEs. Therefore, if you want to run more models at the same time, you have to reduce the individual memory footprint of different models. And for example, systems like Vessels by Kim et al. Would benefit from these techniques. Also, cryptographic methods exist using homomorphic encryption. This is a very active area of research. Although the latency is pretty slow on individual images, you can make up for it by using large batches of data. But existing work focused mainly on user data privacy, not model confidentiality. And if you want to include confidentiality to it, then the performance would drop significantly. Finally, the key takeaways for this presentation are that page thrashing is caused by inefficient access patterns in convolutional layers, and we solved it by using partitioning, while the decryption bottleneck is caused by the size of the weight matrix in fully connected layers, and we solved it by using compression and quantization. Future work should include handling more architecture and layer types. And if you are interested in more details, feel free to visit the CakeLab website at this address. And thank you for your attention, and I hope you enjoyed this presentation.